No class on Tuesday, 22nd April. I'll probably be doing one makeup class. Where is everyone? There are fewer people today, right? One person is on Zoom. Julia is not well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 4 people are missing. Cecilia is missing.
No, I'm here.
Cecilia is there. You have a cap.
Yeah, my hair looks bad.
So does mine. Doesn't stop me. Then who is missing? Oh. Didi is missing. Tucker is online. Tucker is online. Julio comes late. It's okay, we are fine. We'll keep going. Okay. So what are we talking about? We are talking about interacting systems, right? And in interacting systems, our main guiding principle is that there exists an n-body potential, right? Which captures how does every atom or every molecule, how do they talk to each other? What is the interaction energy between all of them? And remember, when I say R superscript n, it's a mega vector that collects everything. And R1, R2, R3, Rn are the vectors of particles number 1 to n, right? So these are all little vectors. I'm not going to draw the arrows. That's why I write them like this. So this is a complicated many-body potential. Like I said, often these days, people even use neural networks for this. So this is super complicated. But what we want to do, and I'm recapping some of the concepts we introduced before we get to new things. What we want to do is we want to talk about the probability of finding a collection of particles, right? If it was independent, thinking about collection of particles would be trivial because probability of finding a collection of particles is simply the probability of finding individual particles, right? So, by the way, if you are interested in statistical physics, today in the I1116 room, Jan Sengers will be giving statistical physics seminar at 1:15. There are many things amazing about him, including that he's 94 years old and still publishing first author papers. 94. It's quite, come only if you want to see how a 94-year-old person can still be really, really passionate about science. He used to be chair of the chemical engineering department here in mid-70s, something like that. Huh? No, I'm done in 2 years. Just kidding. Eh? Yeah, it's fine. I have funding right now. If funding dries out, then I don't know. It's all about funding. For now, it's okay. We'll see. So the first thing we introduced was the probability, P2, of finding particle number 1 at R1 and particle number 2 at R2, where we are distinguishing the identity of both of these particles. And this probability will be proportional to integrating out over the positions of everything else, the Boltzmann factor, U of Rn, right? So this is that probability. Then we said we are interested in indistinguishable particles, classical fluids. So we don't really care about exactly particle number 1 at R1 and exactly particle number 2 at R2. We are interested in any particle at R1 and any particle at R2, right? And we don't care about their identities. This one is going to be larger than P2, right? Because now we have many, many choices. And this is a distribution function. It's not really a probability. And we define this as how many ways can you pick the first particle, how many ways can you pick the second particle. And this becomes n minus 1, P2 of R1, R2. So then we showed that for, we could also define a similar rho 1. So we looked at rho 1 of R and we showed that rho 1 of R is equal to rho, the density, equal to n by v, even in presence of interactions for isotropic, radially symmetric system. And the key thing to keep in mind is this was true even in the presence of interactions. Similarly, we showed that rho 2, and here there is no point in writing R1 or R1 or R2 because it's just R, it's constant, right? It does not matter which thing are you talking about, which particle are you talking about. Similarly, we wrote down rho 2 of R1 comma R2, And this is equal to rho square is equal to n square by v square. Both of these need isotropic radially symmetric systems, but this one is true if no interactions, right? If you have interactions, then the second one is not true. And we worked through this proof. Then we said, well, okay, so what happens to it when there is interaction? We said, don't worry. We will write down rho2 of R1 comma R2 as rho square multiplied by G of G2 of R1 comma R2, where all the business that is happening due to interactions is captured by G2, right? And then we said, well, we are thinking about radially isotropic systems, spherically symmetric. So why do we have to care about R1 and R2 separately? All that matters is modulus of R1 minus R2, the distance between two particles. So that led us to talking about rho2 of R in an interacting system is equal to rho square multiplied by G of R. And this G of R is the radial distribution function. This was the main thing that we wanted to introduce. We took some time to get up till there, but we did. And we developed some intuition about G of R, particularly by looking at rho G of R. Rho G of R was conditional probability. Oh, Samyak is also not in class. He had some presentation and exam and stuff yesterday. Oh, that you just told me you won't be joining.
No, I said yes.
Something. Oh yeah. Oh yeah. Samyak is there. Fine. How was your exam? You also took the exam, right? How was it? You agree? Good. My student Ricky also took it. I gotta ask him. Okay, so conditional probability of finding particle at R given another particle at 0, right? And using this, we developed some intuition. We drew this for an ideal gas. We said for ideal gas, conditional probability of finding a particle is going to be constant wherever you go, right? So it's a flat line. For crystals, we drew those peaks and we got into thinking that the height of the peaks tells us about number of neighbors that you have, okay? And things like that. So we drew all that. Finally, we mentioned that in experiments, what we really measure is S of k or the structure factor. And S of k is the Fourier transform of G of R. And G of R is the inverse Fourier transform of S of k. And Fourier transform sounds very strange when you think about it, but it's really fundamental to life. As I mentioned probably in the first lecture itself, our ears are doing a Fourier transform of whatever you're listening. And somewhere in the brain, an inverse Fourier transform is taking place. Does the brain know math? I don't know. Huh?
Obviously it does.
No.
What are we doing right now? Math.
I don't know if that is math. It is. It's hard to say. What does it mean to know anything, right? Do you all know StatMech? Looking at your homeworks and your midterms so far looks fantastic. We'll see in the final exam whether you know it or not.
All information is subjective, so I don't know why we understand that.
Yeah, I mean, this is a philosophical question. What does it mean to know anything?
Fourier transforms are a social construct.
They are a social construct. The brain can perform Fourier transforms. That is not the same as the brain knowing Fourier transforms, right? So people talk about DNA-based computing, for example. You could use DNA to do computing. What does it mean that the DNA knows how to compute? Not really. You are exploiting that to do something, right? So I don't know about the brain. Okay. Fatma is here. Good. So we haven't done anything new. I was just recapping the ideas from last time. So mostly we got to talking about G of R. So what I am going to do today is to give you some more. So I showed first of all that rho G of R is the conditional probability of finding a particle at R, given there is another particle at the origin. But I'm going to prove another theorem, which is super interesting. Before proving this theorem, let me show to you why do we need to have such a theorem. Okay. So the theorem comes as follows. So let's imagine we have our box. And in this box, we have lots of particles. There is Julio. He's happy. I don't know why, but he's happy. And there is Samyak. He's not exactly happy. He took the exam. There is Disha. She's freaking out because she has to decide grad school by tomorrow. Today? Wait, I thought it was tomorrow. Yeah. Oh yeah, it's 15 today. Good. So she's freaking out. Even though it will all be fine. And that's me. I'm very happy because I have tenure. So that's, so there are all these systems and they are interacting with each other. There are all these particles, they are interacting with each other. When I draw lines like this, it means it's just a two-body interaction, right? But interaction can be collective also. Like if you think about collective interactions are kind of hard to understand, but if you think about it, they matter, right? I mean, it's like saying, can you break down the potential energy in a sum of two-body terms or do you need three-body terms? And if you just have two-body terms, for example, you cannot describe water. You need to have three-body terms to describe, to get the angle correct in water and things like that. So these are all talking to each other and maybe they are complicated three-body interactions also that depend on theta. Maybe they are complicated four-body interactions that depend on phi. So it's a whole mess. But the point I'm asking is, what is the average force experienced between two of these particles? Okay, and I'm going to label these two particles right now. So who was the happy one? That was Julio and Samyak. So we have Julio or Julio? Julio and Samyak. What is the average force experienced between Julio and Samyak, averaging over everything else, right? And this averaging over everything else is quite important because the force they experience will depend if Disha decides to come and sit right in the middle of both of them. Over here, that force is going to change, for example, right? It's completely different. So it depends on what everything else is doing. How would we get such a force mathematically from the n body potential? If I have u of Rn and I'm interested in calculating the force, in general, how do I get force from a potential energy? Mathematically, what do? I differentiate it, right? Force is different derivative of the potential energy. When you go to high dimensions, you have to do gradients, right? So if I'm interested in calculating the force along particle number 1, that is going to be the gradient of the potential energy. More specifically, it will be, if I want to write it down mathematically, what this will be minus partial u by partial r1x along vector x minus partial u by partial r1y along vector y minus partial u by partial r1z along z. Okay, so notice what I've did here. What is Rn? Rn is R1x, R1y, R1z, R2x, R2y, R2z, so on and so forth, right? Rn is a 3n dimensional number. And this gradient differentiates it with respect to R1x, R1y, R1z. It does not differentiate it with respect to R2x, R5y, R8z, things like that. So my question for you now is, what variables does F1 depend on? U is a function of all 3n variables, right? U depends on everything. What does F1 depend on? What does the force experienced by particle 1 depend on? The way I wrote it over here, I'm not averaging over anything else. Huh? Everything, all the coordinates. If U is a function of all the coordinates, by differentiating it with respect to something, I have not removed out those coordinates, right? So another way of thinking about it, let's write down some arbitrary u. If u was x squared plus y squared plus xy plus yx, right? And you differentiate u with respect to x, this thing is still a function of x and y, right? It's possible that if it was only x squared plus y squared, the y term goes away, right? And you're only left with something which is a function of x. But in the general case, just because you differentiate something with respect to one of the 3n variable does not mean it will stop being a function of the other 3n minus 1 variable. They are going to be there, right? So this F1 is the instantaneous force experienced by particle 1 as function of positions of all particles. Okay? I am particularly interested in understanding the force of interaction between Julio and Samyak. Okay, and let's use R1 to describe the coordinate of, if this is my origin, let's say Julio is described by R1 and Samyak is described by R2. And if I'm interested in describing the force between Julio and Samyak, everyone is a sphere in this model. So everything is spherically symmetric. So I will be interested only in the modulus of R1 minus R2, right? That's the function their force will depend on. It will not depend on how I rotate them and things like that. It will only depend on the distance. So the force between particle 1 and 2 will be given by minus gradient with respect to R, I'm being mathematically a bit sloppy here, U of Rn, okay? Where R is equal to modulus of R1 minus R2, okay? This is the instantaneous force. But now I want to do something else. I want to calculate the mean force between particles 1 and 2. What do I mean by mean force? By mean force, I mean I want to take the same force minus gradient of, with respect to R of URN, but average it over all possible positions that R3, R4, R5, R6, etc. might take. Okay, so I am going to wash out over whatever else you all are doing. Does not mean that I'm going to ignore the rest of you. It means I'm going to average out over exactly what you're doing. Okay. Turns out, we will show next that this force comes out to be kT multiplied by d by dr of log of g of r, which is an amazing result. If you know the radial distribution function, you take its log and you differentiate it with respect to the radius, to the r variable, and that tells you the average force between two particles, averaging over something else. So today, we will prove the above relation. And one of the easiest way to, for most people, not for everyone, some people are very, very abstract oriented. So they like proofs first, intuition later. I like intuition first, proof later, before I lose hope. So I'm going to give you intuition for what this equation means, okay, and how we can use it and why it sort of makes sense before we get into the math, okay? So again, we will show later, I will write down the relation, that minus, and a better way of writing it is minus gradient with respect to R of U of Rn, averaging over R3, R4, Rn is equal to kT d by dr ln g of r. This can be written as kT d by dr ln of not ln of, I cannot do that with kT. It can be written as 1 over beta ln of gr, right? Everyone agrees with that? It's just algebra. And this is some sort of force, right? This is the force between particle 1 and 2 averaged over everything else. So we are showing that F1, we are going to show that F12 is equal to d by dr of 1 by beta ln g of r. This ln 1 by beta ln g of r, we are going to give its own name. We are going to call it W of r, or the potential of mean force. This is also a term that comes up in computer simulations and also experiments quite a lot. In other words, we are going to show that, actually this is minus WR. We are going to show that F12 is minus d by dr of W of R, where W of R is minus 1 over beta ln G of R. And you can see from this equation, why is W called for the potential of mean force, right? A force comes from differentiating a potential, right? Once you have a potential energy, you differentiate it, you get a force. Here you are interested in mean force. And this mean force comes by differentiating W. Hence, W is the potential of mean force. Okay, that's the idea. In computer simulations, and in a lot of papers, you will see people just calling this as PMF. Just like radial distribution function is called RDF, people call this, or G of R. Here, people call this PMF. So often, you will just see papers where people say, I'm going to compute the PMF. For example, one of the most important PMFs is sodium and chlorine ions associating and dissociating in water. Again, this is one of those examples. Water matters, right? If you had sodium and chlorine in a vacuum, the interaction force between them is going to be completely different between what you had in water. In fact, in 1950s, the Nobel Prize went to Rudy Marcus, who did Marcus theory for things like that. When you are pushing sodium and chlorine together, the waters have to move. If waters are just stuck in the middle, you're not going to form a bond, right? So the solvation matters, right? So people compute the potential of mean force for sodium, chlorine ion pair dissociation. You can do it for anything of interest. So this is the relation. Let's just call it equation 1 and call this equation 2. So we are going to prove equation 1 in a bit. Before that, I want to give you intuition about why it matters. Why does equation 1 make sense? Why is F12 equal to d by dr of KT ln GR? Why does this equation make sense? That's what we are going to do next, okay? And in order to develop intuition, we'll start with ideal gas, and let's see if it makes sense for an ideal gas. So for an ideal gas, last time you all were with me, we drew the G of R, and anyone remembers what was that? It was a flat line equaling. What was the value? 1. Because multiplied by rho, it should be rho, right? It should be the density. So if G of R is constant as a function of R, and again, let me write down here, I'm trying to show intuition for F12 averaged, really. Let me draw a bar on top of this. This shows some sort of averaging going on. F12 average is KT d by dr ln G of R. So what is if G of R is 1, what is ln G of R? What is log of 1? Huh? 0. If it was not 1, it will still be some constant, right? So log of G of R is a constant. If you differentiate a constant, d by dr of 0 or d by dr of some constant, what is that going to be? 0. So if I draw the corresponding force, F of R, what is that going to be? 0. That makes sense. For an ideal gas, there is no force of interaction, whether you average over everything else or not. It's an ideal gas. Why should there be any interaction, right? So this was for an ideal gas. G of R is equal to constant. And if you use this formula, you get F of R is equal to 0. Makes sense. Okay, let's go one step further. In our pursuit to describe molecules, the simplest approximation we can come up with is an ideal gas. What's the second simplest approximation we often come up with in PChem? Van der Waals gas. What is physically the difference between ideal gas and Van der Waals gas? Hard-sphere interactions. And Van der Waals, so to be, it can condense. So there is, if we have to be very careful, there is ideal and hard sphere and then Van der Waals. Van der Waals also has some sort of attractive force that is going on. So the next approximation would be hard sphere gas. What happens in the hard sphere gas? In the hard sphere gas, you say particles are ideal, but have a finite radius, right? So they can go as close as possible until they start to touch each other. And that's not going to happen, right? That's the whole point. So the first thing is, what is G of R for a hard sphere gas? So hard sphere gas means I have things that have a finite radius A, right? And they are just moving around. So what is, again, remember rho G of R is the conditional probability of finding a particle at R when something is at origin. So what is G of R going to look like in this case? Huh? Flat, that's correct. Let's start with the flat part. How long should it stay flat? When should it stop being flat? So not just flat, it should be zero. If you have a particle over here, the conditional probability of finding a particle on top of it is not going to happen. It's zero, it's basically zero, right? So it's going to be flat for a while. Till what value should it be flat? R is equal to how much? 2a. You are talking about the distance between the center of mass of two particles, right? So it's 2a. Then what happens? Infinity or something else? After R is equal to 2a, these things behave as an ideal gas. So it should look like an ideal gas. So it won't be infinity, it will look like 1, like a flat line. Okay, so it's a step function. So the conditional probability of finding two particles on top of each other is 0 if the distance between their center of mass is less than 2a, and it's uniform if the distance is more than 2a, right? That's the whole idea. Okay, cool. Now we take, so mathematically, this is what people call a Heaviside step function. If you remember any of your math, what's the derivative of the log? You don't have to remember math. If you look at its log, what is the log? This is an interesting one. What is the log of G of R until 0 to 2a? Undefined. And then it is log of 1 is equal to 0. So we are going from undefined to 0. So I guess you do need to know your math. You can go and look it up. The derivative, anyone remembers it? This also happens in quantum mechanics. What is the derivative of a step function? Delta function, right? And the same puzzle must have happened to you in quantum mechanics. It's like, how do you differentiate it? I mean, physically, you can see there is a steep rise, right? It's a rise in a very tight place. It's a rise in an area which is close to 0. So the derivative of this, and it doesn't matter whether you look at G of R or log of G of R, the behavior is still the same. You're going from a nothing to very, very high value, right? So that one is going to look like a delta function. In this case, the f of R. And that makes sense. Basically, the force is ill-defined if you have two particles closer than 2a. Right? You just can't have it, right? That's why it's ill-defined. So if you really had to be picky here, this delta function should be sort of asymmetric, because it's really, if you had to be really mathematically pedantic over here, this delta function should look like this, right? It's ill-defined on the other side of R is equal to 2a. There is no force because you just can't have it. The probability of observing it is 0. And the point is that basically these two particles are moving around happily oblivious of each other until they hit each other. And then there's a very, very strong reaction. They go like, go away, I don't like you, right? So there's a very strong force when they hit each other. Otherwise, there is no force. That's the delta function, right? So that's how, so again, it makes sense looking at this relation. That's the hard sphere gas.
So what does it mean like physically?
Well, hard spheres are not really physical in that sense, right? There will be some tolerance into how much they can squeeze and things like that, you know. So you will end up having a delta function. The width might be asymmetric on both sides. So everything, hard sphere is an idealization that you're not going to achieve it in reality. Even, I mean, the thing closest to a hard sphere would be xenon. Even xenon, at some point, if you squeeze it too hard, the electrons will start doing something, you know. So we can just stay with the delta function. Let's go one step further to a crystal. here I'm going to draw two curves, not just on top of each other. So on the top, I'm going to draw G of R versus R. And then the bottom, I'm going to draw the corresponding F of R versus R. So remember the G of R for a crystal has peaks. It has some peak over here. Then it has another peak. Then it might have a third peak, which might be higher than the first one. We don't know. And if you keep going, at R tends to infinity, even for a crystal, this value will become 1. If even in a crystal, if you go really, really far from each other, at some point the interactions drop out, right? There is no interaction. So any two particles, I mean, you guys have all interaction with each other, but if I took one of you and removed you to, I don't know, Brazil or India or China, and there is no internet or anything, then you're not interacting with each other. Like to all practical purposes, you're two particles in an ideal case, right? So for anything in some limit, there will be peaks corresponding to neighbors, and at some point it will go up to 1. Okay, for this one, how will it look like? So let me draw corresponding lines below this. How should the force look like between two particles? So you can work through the math, or you can also look at it intuitively. When you're on the left side over here, it's going to rise just like the delta function we had earlier, right? And then it's going to drop until it crosses 0. And then it's again going to rise. Again, it's going to drop until it crosses 0. Again, it's going to rise. It's going to drop. It crosses 0, and so on and so on. Okay, until it goes down to 0. So, and all this is saying is, if you have two particles, they want to fall into one of the neighboring shells. They are not just going to hang out. This is like a very, very ordered system, right? So two atoms are not just going to hang out in the middle somewhere. They will, if they are closest to the first nearest shell, they will go over there, right? So this force, if you're closest to the first nearest shell, the force takes you in the direction over there. If you're closest to the second nearest shell, the force takes you in the direction over to the second nearest shell, okay? And you can plot this in Mathematica or MATLAB or anywhere and see that it actually does look like this. Any questions about this? Really?
Could you explain the relative positions of like the forces in the G of R again? Like,
So the question is, does this 0 pi align with the peak? Do I have a shift here?
yeah.
Are you sure?
No, I mean, like that was my question.
I think Chandler has a
It's
plot.
kind
Let's
of
look at
hard
it.
to tell.
I think this is correct, but let's see. If it was no ln, if it was just d by dr should be 0 at a maxima, right? So I think you're correct. Okay, DIY1. How does this look like? For a crystal. Go and do it yourself, okay? I might ask it on the final. Or the next homework. Yeah, it's a maxima. So, but be careful. There must be. I think I have gotten confused about this in the past also. But you get the point that it's going to have peaks and it's going to change signs. Depending on how things go. That's the main point over here. And the bigger point is that if you knew G of R, if you knew S of K from scattering, you could inverse Fourier transform it. You could get G of R, and if you know G of R, you can calculate the force between two particles, right? And if you get the force between two particles, that's quite useful. That's the idea. So in order to, so hopefully this gave you some intuition. Now what we are going to do is to actually go and prove that relation. And so there will be more math now. So what we want to do next is to calculate. Again, let's draw a box. In this box, I have one particle here, I have one particle here, I have a bunch of other particles, and I want to calculate the force between these two particles. Force between two particles averaging over everything else. The other reason I tried to give you some intuition is because the way this proof will work is I'll just start from nowhere. Okay, it will be like, why are you starting from here? And then you will see how the answer comes out, as it happens in a lot of mathematical proofs. Okay, so that's why it's important to know that what we are trying to go for. It's kind of like a PhD. You have no clue why you're doing what you're doing. You might not have a clue even when you defend. And that's okay. So we will start with row 2, which is the reduced distribution function of finding any two particles at R1 and R2, right? What is rho 2? Remember, rho 2 was defined as rho square multiplied by G2 of R1, comma R2, right? This is how we defined our G2. It had some name, interdependence function or decorrelation function, something like that. I don't really care about that name. What I do care is you remember radial distribution function. And I care you remember potential of mean force, which we're just going to talk about. These two you should not forget. The other terms, it's okay if you mess up the names. But not during this semester. During this semester, your knowledge should be at a local maxima. Okay, then it will decay. And that's okay. It will again peak around your qualifying exams. For a lot of people, their qualifying exam is the global maxima of your life, of knowledge. I mean it. It's a very special moment. You'll never know as much as you do the day before your qualifying exams. For most people. Okay, so we have this, and this can be, so I numbered some equations. That was 1, 2, let's call this equation number 3. Equation number 3 can be written as G2 of R1, R2 is equal to rho 2 of R1, comma R2 multiplied by 1 over rho square, the density, right? Rho is equal to N over V. This is again one of their proofs where everything seems to happen in opposite. So we are going to now write down rho as N over V. Remember, rho is equal to N divided by V, the number density. So in other words, G2 of R1, R2 is equal to V square by N square multiplied by rho 2 of R1, R2, right? We will again go one backwards. This is V square by N square. What is the connection of rho 2 with P2? N multiplied by N minus 1 multiplied by P2 of R1, comma R2, right? I'm just using the definitions so far. Yeah, it is tedious. Someone yawned. G2 of R1, comma R2 is therefore V square multiplied by N minus 1 divided by N square multiplied by P2. Why do we care for P2? Because P2 is the one thing we can write down in terms of the potential energy function, right? P2 is integral over R3, dr4, drn e to the power minus beta u of Rn, the full many body potential, divided by the partition function, right? I should also have a 1 over n factorial here. I will call that over here. I should also have a h cut to the power 3n over here in my Q, and depends on how you calculate it. I should also have the lambda n to the power lambda t to the power 3n over here if I really wanted to be precise. Okay, but what I am going to do is to call all of this as capital G. Does anyone know what capital G stands for? It's garbage. It's terms I'm not going to care for. Why don't I care for this? Because in the end, what am I trying to do? I'm trying to differentiate G with respect to R. These things don't depend on R. They look fantastic, but I don't care, whatever they are, right? It's just some garbage. When I will differentiate, they will disappear. So in other words, we have G2 of R1, R2 is equal to capital G multiplied by integral e to the power minus beta u of Rn dr3 dr4 dot 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 drn. And what is q? This q matters because this has the position part of the partition function, right? So this q is the same as e to the power minus beta u Rn, but now you're going to integrate over everything, dr1, dr2, drn. Okay. I will wait for a moment.
Is this in the canonical or microcanonical ensemble?
What do you think?
I'm
Look at
not
the
sure.
denominator.
There's a fixed number of particles, but
Yeah.
there's also temperature and energy.
It's the potential energy function, which is not this. It's a very good question. It's the potential energy function. That does not mean I'm not allowing the potential energy of the system to fluctuate. U of Rn is just a function, right? The potential energy of the system comes from. That's a great. Actually, I'm on the right test. This is wonderful that you asked this. So U of Rn depends on Rn, right? Does this mean that energy of the system is fixed? No, energy of the system can be calculated from U of Rn by doing U e to the power minus beta U dr1, dr2, drn, right? That is the average energy of the system. So be careful with these things, So this is the, this actually happened in my group meeting the other day. So this is sort of the thermodynamic potential energy, if you think of it. So it's a canonical potential. You have e to the power minus beta U, okay? So what I really want to show is equation 2. Remember, I want to show F12 is equal to minus d by dr of W of R, where W is minus 1 over beta of ln of G of R, okay? So this equation that I have over here, equation 4, I'm really interested in ln of G2, right? And I'm not talking about spherically symmetric things. I've kept it quite general. I will make that assumption later. So I'm going to take the log of both of things, of both sides. So equation 4, ln both sides. What will that give me? Ln of G2. But what is ln of G2? Minus beta W is equal to ln of G, right? So ln of G2 is minus beta W. In other words, minus beta W2. W2 is nothing but G of R on a log scale. That's what we are looking at. Minus beta W2, which we have defined as ln of G2, is going to be log of everything here. What is log of garbage? Huh?
Garbage plus log of other stuff.
What does anyone speak French here? What is garbage in French? You are Canadian, don't you speak French?
It's not French, it's Quebecois.
Oh, terrible. My PhD advisor from Quebec. So it's just some garbage, right? So this is log of G. When we differentiate it, it won't matter, right? Because we are going to differentiate. What are we going to? We are interested in derivative of W with respect to R, right? So whatever log of garbage is, we don't care, because when we differentiate with respect to R, this does not have any dependence on R. It's all integrated out. Plus log of the numerator in equation 4, okay? log of the numerator in equation 4, that is log of integral dr3, dr4, drn. Is there a scientific question or people talking about garbage?
It's poubelle in
I
French,
believe you.
but it also means trash. So
Oh, cool. In Hindi, it's kacha. And then minus log of the partition function. Does the partition function depend on R? No, it's again integrated out, right? So in the next step, what I'm going to do, I'm going to do minus beta gradient with respect to position of R1 of W2, which depends on R1 and R2. Okay, so I'm doing a gradient with respect to coordinates. And if your multivariable calculus is funky, be careful to go back and check this operation. What does gradient with respect to R1 mean? You know. So when I do this, this one will give us 0 because it does not depend on R1. This one will give us 0 because it does not depend on R1, right? So the only thing that will left will be this one. So we have to differentiate this thing with respect to R1 and multiply it with, well, just differentiate it. So how do we differentiate this? Well, we have to use product rule. So d of log x by dx is 1 over x, right? First thing. So the thing that we have inside the log will come in the denominator, right? So you will have integral of e to the power minus beta u of Rn dr3 dr4 dot 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 drn, and then you will go inside the integral and differentiate it with respect to R1. dr3 dr4 drn are not R1, they are everything else except R1, right? And so that's going to be integral of e to the power minus beta u of Rn multiplied by minus gradient with respect to R1 of u of Rn. Chandler goes through this proof, by the way, so this is clunky, please go through it. Multiplied by dr3, dr4, drn. Okay, we are basically there now at this stage. Let me write down this equation more carefully, slightly on the next page. Pause for just a moment. Okay. So what I've just shown is that minus gradient with respect to R1 of W2, which is the log of G of R multiplied by beta or something like that, R1 comma R2 is an integral that looks like e to the power minus beta u of Rn. In the denominator also, you have e to the power minus beta u of Rn, but there are two key differences. There is only one key difference, that here there is something else. In the denominator, you just integrate this over dr3, dr4, drn. Here also you integrate over dr3, dr4, drn, but you multiply it with a gradient with respect to R1 of the full many-body potential that depends on all atom positions, right? Now, if you remember anything about your canonical partition function, this is like an ensemble average in the canonical partition function, where you're averaging over all particles 3, 4, 5, and n. Notice there is no R2 here. It's like we have been mean to R2, right? We are differentiating with respect to R1, and we are averaging over R3, R4, Rn, and we ignored R2. We did not really ignore it. We are carrying that explicit variable. R2 is going to stay in all of this. So this is the ensemble average of the quantity gradient R1 u of Rn averaged over all particles 3, 4, 5 up to n. Okay. And what is this? This is F1, if you look at this thing, this is how I started by defining, right? If you have the n body potential function, and if you take the gradient with respect to the coordinates of particle 1, that is the average force experienced by particle 1 averaging over everything else in 3, 4, 5, ... n. So it's a bit subtle. Note how we are treating 2. It's like we are looking at 1 together with particle 2, and we are keeping the 2 wherever it's going to be. We are averaging over everything else. Okay, so 2 is not being averaged out. More importantly, we are interested in f of r, where r is modulus of r1 minus r2. There, this confusion becomes a bit clearer. We are not just interested in particle force by particle 1. By the way, will f1 bar be the same as f2 bar before we get into the spherical symmetric case? That brings me to, what does it bring me to? DIY2. DIY2. Is f1 bar equal to f2 bar? Think about it.
Should we go 7, 8?
What? What do you want?
No.
You want something? Tell me, what do you want?
No, it's just the numbering of the DY.
Oh, DIY for this class.
Okay. The answer yes.
I don't know. I just came up with the questions. I don't know. You're going to solve my curiosity.
Wait, what's that again? D bar
DIY
of
2 is f1 bar is equal to f2 bar. What do I mean by this? Or is there a minus sign? I don't know. Because Newton's third law of motion says equal and opposite forces, right? Here, this is sort of like Newton's third law of motion, but it's averaging over something else. So I'm asking, does Newton's third law of motion apply when you're averaging over everything else? What do you think, Samyak? Should? But I want you to mathematically prove this. It might be trivial or it might be profound. If it's profound, you can write a paper together, okay? So what we are more interested in is f of r, where r is modulus of r1 minus r2. And this thing is well, wait a minute. Give me a moment. I want to confuse something here. Okay, so this this is what we are interested in, right? So in order to do that, let's go to our equation 5. And let's write down equation 5 a bit separately. So this is Chandler section 7.3. So what I've just shown is that minus d by dr1 of u of rn, keeping r1 and r2 fixed, averaging everything else, okay? That's what we are really doing, is equal to kbt d by dr1 of ln g of r1 comma r2. This is what we have shown. Let's call this equation 6. For spherically symmetric system, this shows that minus kbt ln of g of modulus of R1 minus R2, because for a spherically symmetric function, g of R1 comma R2 will really be g of modulus of R1 minus R2, is a function whose gradient gives us force between particles 1 and 2. So this already answers your DIY2. I've just switched from force on particle 1 to calling it force between particle 1 and 2, but I still want you to work through it, right? It's going, Newton's third law of motion is still going to, we have not violated Newton's law here. Yeah, go ahead.
Say like R1, R2 fixed, something like
R1, R2 fixed, averaging everything else. Wow, that's really terrible handwriting. Let me write it a bit cleaner. Averaging, slightly cleaner. Everything else. Okay, so if g of R1, R2 was really only dependent on modulus of R1 minus R2, this shows you that the force experienced by particle 1, force experienced by particle 1 is going to be equal and opposite of force experienced by particle 2, which you are going to work through in DIY2. There is not really anything to work through. You see, it's the same thing, but still do it. This is the force between particles 1 and 2, right? Therefore, W of R is equal to minus kbt ln g of R is called potential of mean force. Okay, this is what we wanted to show. Any questions about this? Gives us force between particles 1 and 2. It seems to me that my math is easier to read than my English. Like both the questions you guys asked so far were on the English part, so I should just not write English. This part I copied from Chandler because I wanted to be precise in the text. Okay, good. So until so far, we have not assumed a particular form for U of Rn, right? We have just said it's some many body potential. Even though we talked about spherically symmetric systems, we did not say whether it's restricted to only two body interactions. It could be 3 body, it could be 4 body, it could be anything, right? Going forward, what are we going to do next? We are going to keep building on this. We are going to agenda from here onwards. Not just today's class, but also Thursday's class and stuff. First thing we are going to do is, I had mentioned earlier how to get that G of R contains all thermodynamic properties. And I will show you how to get thermodynamic properties from G of R. You already saw something like the average force, which is like a thermodynamic property, right? The average force expression was valid for any interaction. But here we are going to assume the part that I'm going to derive next, that U of Rn is a sum of two body interactions. So I is equal to 1 to n, j more than I to n, some small u that depends on Ri minus Rj. So I'm going to assume this form for the potential energy. Okay, I will not really assume much about what exactly is U of R. U of R could help. Everyone knows in quantum mechanics there is a perturbation theory, right? Is there anyone who does not know perturbation theory in quantum mechanics? There is time-dependent perturbation theory, there is time-independent perturbation theory. Which one is messier? One of them is ugly, right? Which one? Time-dependent one, right? I remember it's.
Anytime you add time to it, just get rid of that.
Is there anyone here who likes Klebsch-Gordon coefficients? I hate you. That's horrible. Yeah, well, if you're doing certain types of research, you better not hit them. You better like them. I found them really, really painful anyway. So, but we are not going to do Klebsch-Gordon. What we are going to do is statistical mechanical perturbation theory. And this has a deep connection to Maryland. Statistical mechanical perturbation theory, the father of this was someone named Bob Zwanzig or Robert Zwanzig. Has anyone apart from Disha heard his name? Disha has heard his name way too many times. No one? Have you? Oh, you came to that seminar, so you also know it. Has anyone here been to IPST room number 1116? The seminar room, older seminar room next to my office. That used to be his office. He was a professor here for around 20, 25 years. And then Maryland Physics hired someone named Michael Fisher, who is also very, very famous. When I did my job interview here, Michael Fisher came to my talk. Michael Fisher nearly got the Nobel Prize for something known as renormalization group theory, which we are going to cover in a couple of weeks. The actual Nobel Prize went to Ken Wilson. Somehow Michael Fisher did not win it. If you read Ken Wilson's Nobel lecture, he says how much Michael Fisher inspired him. So when Michael Fisher was hired, Zwanzig got upset. I guess that's how academics are. And he left for NIH. But in 1950s, Zwanzig wrote a series of 5 papers which introduced this perturbation theory. Around the same time, Feynman also wrote a similar paper about slow electrons or polarons or something like that, which has the same idea. And these 2 papers will be in the second midterm. You will have the chance to go through these papers. And Zwanzig introduced this idea of perturbation theory, where the idea was, you know, how we have been talking about non-interacting systems. And we suddenly jumped to interacting systems, right? We went from everything is oblivious of everything to many body positions where everything is talking to everything at the same time. Could we find some sort of common ground? In other words, could we have a hierarchy of interactions? We sort of turn on the interactions. We start with an ideal gas, and you saw we went from ideal gas to a hard sphere, right? So you could imagine going from an ideal gas to hard sphere. How would you do that? You would introduce the value of A, right? For an ideal gas, A equals 0, right? So you will do some perturbation theory where A suddenly becomes higher and higher and higher, right? So that's how you go from ideal, you're turning on some interaction, you go to a hard sphere. Then you say, oh, I'm going to make it even more complicated. I will turn on spherical asymmetry and things like that, right? So could there be a way of calculating the properties of a complicated system by actually studying a simple system? And we will show how this allows us to derive the van der Waals equation state from an ideal gas, things like that. So Zwanzig did all this in 1950s, and it kind of disappeared. So in 1950s, there is paper by Zwanzig and Feynman around the same time, independent of each other. Then it kind of disappeared, at least in chemistry. In 1980s, someone named William Jorgensen, who is a professor at Yale, revived Zwanzig's ideas in the context of something known as free energy perturbation. And we will see what that is. You will also have a paper on this. And this became a super hit. Free energy perturbation, which people also call FEP, is a way of doing computational alchemy. So what people do, this idea that I mentioned, that you can change from one interaction to another, people can do it for drugs also, right? You want to calculate the binding affinity for a drug for a protein, and the drug looks very complicated. You gradually start to turn down the interactions, and you calculate the properties for something else. And this FEP became huge. There is a company called Schrodinger. I'm on their board of advisors. This is a NASDAQ traded company. Its market cap is around $5 billion or something like that. They sell FEP. for like $80,000 a year or something. And every pharma company uses FEP to design drugs to screen through billions of compounds. And this all goes to Zonzig. When Zonzig did it, he was not here. Zonzig was here in the 70s or something. So next time you go to 1116, you should know you are like in hallowed grounds. You know, that was the office of Zonzig. So we will be studying all of this. First, we will start with thermodynamic properties from G of R. We'll show how it works. And then we will derive the relation for perturbation theory. It's actually alarmingly simple, how nice it looks. And it's super powerful. We'll do it on pen and paper in our class for Van der Waals equation. Of course, FEP tends to be useful when you do calculations on a computer. That's where it's really powerful. And in your midterm, in your second midterm, you will have a range of papers to choose from. And you can already, I have already mentioned you some of the papers there will be there. There will be a paper on path integral molecular dynamics. There will be a paper by Feynman from 1950s. There will be Zonzig's paper. There will be a more recent free energy perturbation paper. There will likely be a paper by someone named Dan Frankel, used to be at Cambridge, about how you can get complicated interactions in systems, how you can get complicated behavior in systems with only hard sphere interactions. You would think hard sphere is boring, but actually hard sphere is super interesting. And you can get all sorts of very strange behavior. There will be 6 or 7 papers. What I'm going to do is to break you into teams that I will be assigning, and rest assured, so like Rachel and Max won't be on the same team because they hang out together. And who else hangs out? Cecilia and Amy won't be on the same team. So the idea is to mix people, you know. And there will be teams of 4. And what you will be doing is to fight each other over which paper to discuss. One of you will have a strong opinion. This paper is the most important paper, and they will have to convince each other. You will have to form consensus on one paper. And then you will be discussing that paper as a team and submitting individual reports on that paper that you came to conclusion as a team. Now, if you really like one of the other papers and you decide to write a report on that paper also, you can do that. I won't give you any more bonus points. It's up to you, okay? So I will release these papers. I need to cover Zonzig's thing, which I will do next lecture. And then I will release the papers probably over the weekend. You will have 2 weeks to do it. 22nd, next Tuesday is not a class. So use that time to do the initial round of writing, which paper to discuss and things like that. And it will be a 2-page report, nothing complicated, but it's your, the other reason why I'm going to mix people from different, backgrounds is, so I'm going to maximize your chances of there being arguments in your group over which paper to pick, which will force you to like go over all 4 or 5 papers, okay? Otherwise, you will just pick one paper. Like all the biophysics people will just go to the free energy perturbation paper. And that's kind of pointless, you want to discuss the other things. So we will meet next Thursday. Any questions about any of this? Okay. Bye-bye.
My